That's what happens when we make acids, all right? And because we have these free-floating ions, we have electrons that are released into a solution. And as a result, the ions can, the solution can then conduct electricity. Okay, so water is used to make acids, and why? And it's because water is polar. So I've already shown you this, but the red parts of this are oxygen, and the white parts are hydrogen. Because they're polar, there's a big difference in electronegativity between oxygen and hydrogen. They can make hydrogen bonds, and that's what gives water its unique properties. So make sure you take a look at this slide. This is slide number 19. All right, so we have just a quick review from Science 10, right? Water will allow cohesion and adhesion. So hydrogen bonding is responsible for both of these. So cohesion keeps water molecules together, and adhesion attracts water molecules to other things that are polar. That's what creates things like electrostatic force. So because of water's polarity, it has a really, really high boiling point. It's solid, freezes, and is less dense than its liquid, which makes life on Earth possible, right? But it's what is used to make acids. So this is early theory with acid-base theory. So Arrhenius thought that any acid would make hydrogen. So when any acid dissolved in water, it would make hydrogen, and this is a conjugate base. All right, so the A part would be the conjugate base, and then all bases dissolve to make hydroxide and a cation. Now he's not totally wrong, but he's also not totally right. It's not the whole picture. Okay, so we've balanced equations, and we need to understand that acid-base equations follow the same rules of the law of conservation of matter. I'm not going to balance equations again here, but you guys know that that you need to be able to balance. So Arrhenius, now in your textbook, talk about titration later. So this stuff starts on your textbook, page 165. Right, so, and again, just some general information here on page 168. You should know what acids and bases do, right? So both of them conduct electricity because they make ions. Both of them are corrosive, but you should know that acids turn litmus red, right? They'll react with, acids will react with metals to produce hydrogen gas, so they bubble, and you can see that. They're neutralized by bases in basic solutions. They taste sour, and you can see the difference with bases. They're slippery and neutralized by acids, taste bitter. Okay, so that's page 168, and you need to review that. Okay, so this is Arrhenius, page 170. So page 171 here. So Arrhenius, so some problems with Arrhenius. He stated that hydroxide needs to be present to explain the properties of basic substances, or hydrogen needs to be present to explain the properties of all acidic substances. So you don't always need hydroxide and you don't always need hydrogen. What we do need is we need something that can accept a proton and something that can get rid of a proton. So and so this is what we understand as how acids and bases work, all right? So and a proton meaning a hydrogen ion, right? Because it has one proton. So the proton is subjected with is interchangeable with hydrogen in this case, right? So remember, water is polar, right? And it can, so we can have hydrogen bonding, right? Water can hydrogen bond with the H and make hydronium. And hydronium is your basically your measurer of acidity. Okay, so anything that can accept a proton will be a base. Anything that can give a proton away will be an acid. And this is Bronsted-Lowry acids and bases. Okay, so make sure you take a look at this slide. Okay, so that's what we have. We have a proton transfer and we have a proton acceptor. And when we look at Bronsted-Lowry acids and bases, so this is hydroiodic acid. So you have the acid proton donor and the base proton acceptor. So in this case, it's water. So what happens is the hydroiodic acid will donate a proton to the water and make hydronium. And the hydroiodic acid will have its conjugate base left over. So the conjugate acid is the charged hydronium, and the conjugate base is the leftover ion, and that's I negative. Okay? So we call this proton hopping, all right, or the Grotthuss mechanism. So the hydronium doesn't stick into one water molecule. It'll move and it's dynamic, and that's not a true bond. So the acidity is always constantly changing, but it's that concentration of hydronium that's important. So in your data booklet. So you guys who've been in Chem 30 will recognize this, but this is an acid-base chart, and you need to be able to use this. So what we have here on the top left-hand corner are our strong acids. Okay, and on this, what happens here is as we go down the left-hand side, we have a decreasing strength of acidity. So strong acids are up here. Actually, these three, HCl, H2SO4, and HNO3 are part of our big 6 acids that all make hydronium. The rest of these are combinations of weak acids. So you have the acid with a conjugate base. Now what happens on the right-hand side of this is so you can see this is our strongest base, which is OH negative, and actually H3O plus on the left-hand side is our strongest acid. Okay, so because HCl and H2SO4 and HNO3 will make H3O plus. So OH negative is our strongest base. And from here, you can see increasing strength of base on the right-hand side. So as we go from the bottom to the top, we get weaker bases. So they are conjugates. So the stronger the acid, the weaker the base, and the stronger the base, the weaker the acid. And that's how you read that chart. So you should be able to rank that type of stuff, okay? So the last thing I'm going to do today, I'm going to show you how to make these Bronsted-Lowry acid-base equations. And just give me 1 second here. Okay, so let's say we have nitric acid. So this is HNO3. Now if I go back to my acid-base chart, okay, these top 3 acids will all make hydronium. So HNO3 makes H3O plus. All right. So let's say this is in an acidified ecosystem. So we have acid precipitation making hydronium, and the hydronium is being contributed to the environment. Okay? So let's say this H3O plus falls as acid precipitation. Okay, H3O plus, and it is going to react with, so let's say this is in the Bow River, and we have calcium carbonate as our bedrock here, right? And remember, this is Ca2+, and and this is CO3 2 negative. Now what you can see here on your chart is that we have CO3 2 negative, we have HCO3 negative, so hydrogen carbonate, and we have carbonic acid. So you can see that this is a weaker acid than the H3O+. So the H2CO3 actually will have a higher pH than anything that will make H3O+. Because the carbonic acid, when it dissociates, will make H3O+, but it won't make as much as nitric acid. Okay, so you can see all these three guys all make H3O+. And all of this HNO3 and H2SO4 and HCl, when it reacts with water, all of it will end up turning into H3O+. But with H2CO3, the H2CO3 holds on to that hydrogen and won't make as much hydronium in solution. Okay? So, so this CO3 2 negative, so this is what we're going to call a spectator. So I don't need to use the cation because it's not participating in the actual equilibrium. But what happens here is we can take that hydronium and the acid donates a proton to the base, and the base takes on the proton. So this becomes HCO3 negative, and then what's left over is H2O. So this acts as a buffer. Okay? Because we remove H3O+. And that's what we want when we're dealing with acid precipitation. We want bedrock that can buffer. Okay? So I'm going to talk about things that we are using to clean up acid precipitation tomorrow, and those are different slides, and we'll talk about smog. Well, one way that we deal with acid precipitation is by liming, and we add limestone, which is calcium oxide, or calcium carbonate, right? And it does this reaction right here. Okay. So let's say we have this. Let me give you another buffering example. So let's say we have the carbonic acid, and this is something that happens naturally in our body. Let's say we have H2CO3, and it's reacting with water. So the carbonic acid can donate a proton. Okay, and when we make carbonic acid as part of a buffering, so when we make an excess amount of CO2 in our bloodstream, we'll make carbonic acid, and the carbonic acid will make some hydronium in the bloodstream, and then this affects homeostasis. So this is what actually happens when we exercise at a maximal level and we use anaerobic glycolysis. So this is the ability to clear lactate. So the acid donates a proton and the base accepts a proton. Okay, and that's something that we really do need to understand to be able to do our project. So here's some practice questions. So let's look at this. This is page 171, 12 and 13. And I'm going to do a couple of these examples. So first and foremost, if we look at question 13, it says use the equations written in question 12 to predict whether each solution is listed acidic, basic, or neutral. So I can tell you right now, if you look on your chart, you'll be able to tell. So HNO3 is an acid. H2SO4 is an acid. H2S, you can see this, hydrosulfuric acid, is an acid. NaOH is a base. Na2CO3 is a base because it makes CO3 2 negative. Na2SO4, SO4 2 negative is a base. Now NaCl is neutral. NaCl does not exist on this chart. There's no Na plus. And this Cl negative is really, really weak. It's weaker than the strongest acid. And this is my weakest base. This is called the leveling effect of water. Because everything's dissolved in water, Sometimes there are things that are weaker bases than water and they don't actually participate in an acid-base reaction. So in this case, the Cl negative is actually a weaker base than the water, so it won't accept protons and water will. So let me give you some, let's do these ones here. So let's do HNO3. When they dissolve with water, so HNO3 is one of those big 6 acids. It's above H3O plus, okay, on my acid base chart. So it's actually a strong acid, so it makes H3O plus. Okay, so here's what happens when H3O plus, so this is A, and this is page 171. So H3O plus reacts with water. Okay, this is going to donate a proton. So we're going to end up with H2O plus H3O plus again. So this is really acidic. The acid makes more acid. Okay, if I look at B, that's H2SO4. That's also a really strong acid. Okay. So the H2SO4 also makes H3O plus. So this is the same answer. Okay, but let's look at H2S. Okay, when H2S, so I'm going to look at, so I've got my H2S, and it's going to react with water, and it's going to make a conjugate. So if I look at H2S plus water, okay, this is an acid, and when we lose a proton, it ends up a negative ion. So I have HS negative, which comes from this, and then this makes, right, the proton goes here, and it makes H3O plus. Okay? Now D, and again this is page 171, NaOH. This makes Na plus and OH negative. So we need to dissociate this first because hydroxide is what we're dealing with. So when I have OH negative, so I don't need that. That's not part of my acid-base equilibrium. And I can confirm that because it doesn't exist on my acid-base chart. Okay? So OH negative plus H2O. This is a base, and bases accept protons. So this actually becomes H2O plus OH negative. So the NaOH makes water very basic. Now I can look at Na2CO3. So this is ENA2CO3. Again, I'm not going to deal with the sodium. Bases with sodium, we don't deal with it when we look at the acid-base reaction. So this makes CO3 2 negative plus H2O. And this is going to make, so again, the water acts as the acid. And you can see, right, okay, so you have CO3 2 negative, which is my strongest base. Okay, and I don't have anything else, so the water is my acid. Okay, so the water will be my acid. All right, so I'm going to look for those things. Okay, so CO3 2 negative is my base on this side, and then I look for where my strongest acid is. My strongest acid is down here. So this is my acid. That's my base. So this is going to give a proton to the CO3 2 negative. And we end up with HCO3 negative plus OH negative. Okay. So this is my conjugate acid now, and that's my conjugate base. All right. So this will, because we make hydroxide, this will end up being a basic solution. So Na2SO4 will be really similar to Na2CO3. But if I look at F, NaCl, this will be neutral. Because if we make Na plus and Cl negative, and there's nothing on the chart for that. All right, so that's how you make Bronsted-Lowry acid-base equations. All right, I think I'm going to end the lesson today. We'll do some more stuff tomorrow, but this should be more than enough information for you guys to get started on your assignment affecting factors for acid-base precipitation in Alberta. Any questions, let me know. I'll be back tomorrow with another lecture. Bye now.